Hi, my name is Melanie Warrick. I'm here to talk to you guys about how to run neural nets on GPUs. So I'm a deep learning engineer at SkyyMind. SkyyMind is a startup. There's like 3 of us, and we basically are building a neural net platform. This talk is not necessarily to tell you all about SkyyMind. I will show you a little bit of code from our code base, but primarily what I want to do is cover what neural nets are at a very high level. I'm going to try to give you some understanding of what GPUs are, and then I'm also going to show you some code. I'm going to show you a little bit of code in terms of how you interact with the GPU, as well as show you a little bit of code about how to build out an actual neural net. How many of you have actually applied a neural net before? All right, great. How many of you have used GPUs before? Okay. How many of you need a nap? All right, so this talk is going to be fairly high level. You may already, it looks like a number of you may already know some of the things I'm about to cover, and I'm also very welcoming if you have any input at the end, depending on how the time goes. So in terms of the talk, I'm going to start out, like I said, to talk about what neural nets are. And specifically, I want to take you through sort of the operation, how it functions. And this is extremely simplified. But ultimately, they are a machine learning algorithm for pattern recognition or pattern or prediction. And basically, this idea was born off of the brain. It's not that you are completely simulating the brain, but it's a very rough, abstract concept of the brain functionality. Specifically, if you think about neurons firing and synapses connected and transforming data. And as I speak, actually, there are neurons that are firing in my brain, and they're interpreting data and passing that data along until at some point there's some type of understanding and some type of result that's coming out of it. So that, again, extremely simplified, abstract. And that concept was applied in an artificial neural net in terms of saying, OK, well, we're going to have some inputs, and we're going to transform those inputs and have some type of result at the end. And what you see up here in terms of this diagram is the green nodes are representing an input. You've taken some data, you've translated into a numerical representation. The blue nodes are representing the computation, where you're doing your processing of that data. And each node is doing its own type of computation and interpretation of the data. At the end, that orange node is really giving you a sense of what's my result. And where we're seeing a lot of the actual real value for neural net applications are in supervised learning. This means you actually know what the outcome should be. You know what the answer should be. You've got your math textbook, you're trying to do an equation, and you look in the back to get the answer. So by doing that kind of error checking, you can go back into the neural net and into these computations and make changes to them and tweak them and tune them to get them to fit and model whatever problem you're trying to solve. And how you change that is that, as you can see here, I've got this equation highlighted on the side. And that one is your linear transformation. This linear transformation is typically what you will have on every single node that's in this net. And that linear transformation is basically saying, all right, I'm taking in an input, or several inputs, really. And that's what X is representing. It's representing multiple inputs that are coming into just one node. And then it's applying several weights and multiplying those weights, summing that information together. And then it's applying, there's an additional function that's being applied that I don't have actually up on the slide, but it's usually known as your activation function. And so combining all of those computations together, you're basically going to determine what signal will this neuron send off. What signal will this specific blue node send off to the rest of the net? And that's really what's going on throughout. And this is very simplified, this structure that I have up here. I mean, technically for a neural net, you could just have one neuron. But typically, when you're working with them in real-world applications today, you're going to have easily hundreds in just one layer. And when I talk about a layer, I'm talking about that vertical representation of the blue dots on just one vertical representation. That's a layer. You could have 100, you could have thousands, you could even have millions. I wouldn't be surprised if some people are going even further than that based on whatever type of structures they're building. But I'm just trying to give you a sense of just sort of an overall how this functions, what's going on. And the real key to hone in on in terms of where this has value is as you build this and train this and you change those weights, that's where you start to make this fit the problem you're solving. Okay, hold on to that thought. We're going to come back to it. So why do you care? Why do we want to know about neural nets? Why would we even want to use neural nets? Well, why we care about them is because they're playing a significant role, especially in the areas of image processing and language processing. These areas are great in terms of the type of data that you have, that you can interpret that data and model that data with very rich feature sets or attributes about that data. So neural nets are being applied to things like talking to your phone or self-driving cars, image recognition. If you have any kind of interesting software that is able to identify people or objects in the images that you put into it. It's also taking shape, though, in solving some other interesting problems, and I think this resonates more with this crowd, actually finding anomalies, anomaly detection. Somebody was telling me about a windmill farm that uses neural nets to identify when a windmill is about to break or any kind of issues that might be going on in the functionality of the windmill and the mechanics of whatever's going on with the windmill. It's also pretty popular in terms of financial models, but where it really is resonating, I think, mostly with companies is around things like recommender engines and ad placement. And more specifically, things that are going to be around personalization. So being able to take in a lot of information about your users or your customers and finding ways to pattern match and more uniquely interact with those users, but through models. Good, bad, or indifferent, you can decide on that, but that's where neural nets are going to start to resonate more and more with companies and why they care about maybe spending some money on implementing them. So how neural nets are playing more of a role nowadays is because, or how this equation is actually coming up a lot. I mean, you hear about deep learning, and that's really neural nets, actually. But you hear about it a lot when you go to different tech conferences. And the reason why it's playing such a significant role and why we're seeing real results from it is because Moore's Law has allowed us to have significant increases in our computational power just in the last 10 years alone. These ideas around neural nets and how they function has been around since the 50s. It's just that we finally are starting to see the technology catch up and show us that we can apply it in a way that we want to. Additionally, we have, and I know this is a jargon that gets thrown around a lot, but we do have big data. We have a lot of data that is stored, and we have a lot of labeled data that is stored. Mechanical Turk has allowed us to label a significant amount of data. And so that's helping us to actually see some real results in these neural nets and understand what we want to get out of them. To really kind of hit home in terms of what's going on with this structure, how it works, how you want to think about it functioning. This is an example of a computer vision problem. And this computer vision problem is basically taking images, and I'm trying to predict who this person is. So I take an image of a person, and I'm breaking that image down into pixels. I'm going to convert each pixel into a number, and that number will represent how gray is this pixel. That's what I input into the actual neural net. From there, I have multiple layers. I've overly simplified how this structure would be in terms of computer vision because I really don't have enough room on the slide. But each layer is representing different features that you would look at inside of this picture. And you have one layer looking at edges, for example, different edges. And we could say a portion of an edge of a picture in maybe one would be recognized in one of those nodes. And so each node would represent different portions of the picture. Another layer would look at object parts like a nose or an eye or an ear, and another layer would look at faces, specific faces. And based on whatever inputs are being signaled from the previous layer, let's say we're looking at that object parts layer, we got a nose and we got an eye and we got an ear, and those are the signals that are going into the face layer. We'll say, wow, it's like a puzzle. We're starting to see the pieces. We think this is actually the layer. We think this is this face. We think it's Einstein. Now, that's not Einstein. We know that. But we know that we at least are starting to get some kind of result out of this net, and now we need to train it. And to train it, we will go back with the errors that we've calculated and update our weights and try to make this model more accurately predict and classify what we want to get out of this net. So that's to just give you a sense of how to think about the net, how to think about how it functions, what's going on inside of it. The biggest challenge, even though our computational power has taken off over the years, is that training time is still our bottleneck. That's where we're really hitting against the wall. And people will spend easily like days, sometimes weeks, even months, maybe years, potentially training some of these neural nets. Because the reality is, when you start to talk about these structures and how large they are and how many moving parts there are, and there's a lot of moving parts, a lot of parts that you can start to tweak and tune to make these models fit, the training time is significant. So in order to make that improve, there's always ways to find things to go faster. And that's why GPUs are playing a role with neural nets nowadays. GPUs, graphical processing units, used to make what you see on the screen show up on the screen. That's where they've been primarily focused, but there's a lot of researchers that are starting to use them more and more in terms of doing computations because they're good with floating point operations in particular. They're good with parallel processing. So GPUs are your laborer, while CPUs are really more of the decision maker. I think most of you will probably already know some of this, but really CPUs, they're great. They've got a lot of memory. They have faster clock speed. But depending on the type of problem you're trying to solve and the type of calculation you're trying to do, GPUs can really shine. And neural nets are a great example of where they play a fantastic role because there's independent calculations, independent kind of math, and there's a lot of data you want to process. So if you can split it up correctly across the GPU, you can make things go pretty fast. And specifically, there's a great example that Google did back in 2012 called Disbelief. And specifically, he used about 1,000 servers with 16 CPU cores on each server. Ultimately, they ran this model to watch a bunch of YouTube videos. And the idea was we want to see if we can identify certain objects. It became known as sort of this model that was really good at identifying cats. It actually could do other things, find other objects than just cats, but that was, of course, the thing that resonated the most. Ultimately, they, as you can see, spent $5 billion, and after a week, they got some great results. But then, of course, Stanford and actually Baidu also came along, and we're like, we're going to see if we can do this with the GPU. And I think you all can already see, with 3 GPUs, they basically used a lot less resources, and if they'd thrown probably a few more GPUs at it, probably would have spent less time to just get the same type of results. So you can save time and money, and if you want to really get serious about applying a neural net in a company you're working with, that's why you want to spend some time understanding how to do this on a GPU. So just to level set, in case there's anybody here who has not worked with a GPU before, I just wanted to give some context around certain terminology to be aware of. Specifically, if you're working with GPUs, usually you're working with an NVIDIA or an AMD card. They are the manufacturers that you usually go to. NVIDIA is winning the race in regards to using GPUs for neural nets. Usually, and the reason why is because they've spent a good amount of their time and effort towards developing some pretty good software to integrate with the neural nets and with the GPU cards they've built. CUDA, cuDNN, which is basically CUDA integrated specifically for deep neural nets, cuBLAS, which is for especially the matrix math components. These are software drivers that they've built out to make it easier to integrate with their cards and with their chips. OpenCL is the alternative in terms of a driver to integrate with chips. It's open source, and it actually works also, it works on GPUs, it works on both AMD and NVIDIA, and it also works on CPUs. It just hasn't received as much love and attention, frankly, for development. I think there's some work to try, there's some efforts to try to combat, making CUDA not be the only leader in this space, but frankly, neural nets are still a bit of a niche, and that's preventing, I think, some of the development that we could see in that space. But if you have any interest, you should jump in. Okay, so let's talk about a little bit more about why you would use a GPU. And the way I'm going to do this is I'm actually going to approach it from where the challenges are with a GPU. And specifically, the challenges you're going to hit up against are moving data onto the GPU. And I think some of you are probably pretty familiar with this. Memory limits, because the reality is based on the register size for GPUs, usually you're hitting up against about a 4 GB memory. I think they've done some configurations that allow you to get up to 12, but you have to be cognizant of that memory limit. And then branching, because GPUs like to do parallel processing. So if you've got branching code, that's where you're going to start hitting some issues and really getting your performance. Now, Let's talk about moving memory. So here's the thing, right? You're working with a GPU, and when you're working with a neural net, you're going to probably be working with easily gigabytes, most likely terabytes, and sometimes petabytes or more in terms of the data size that you're trying to process. So this, of course, is starting to touch on, well, so the thing is, first you got to get the data onto the GPU. And to be able to get the data onto the GPU, you have to take it from the CPU's memory onto the CPU, move it over to the GPU, and then move it into the GPU memory. We got latency issues right away. There's some efforts, and unfortunately the diagram's falling off the screen there. But there's some efforts underway, mostly from the software side, to make this seamless and to optimize how the memory is being moved back and forth, or how the actual data is being moved back and forth between the memory, in addition to potentially doing some pointer sharing between the CPU and the GPU so that the CPU can access the GPU's data at certain pointers. I'm actually not going to dive too far into this, but just making you aware that latency in terms of moving data on and off is an issue. Drivers are being developed, and hardware is being looked at in terms of how to make that go faster. And you want to think about that when you're working with it. And as I was starting to kind of dive into, memory limits are your next problem as you're talking about how much memory are you working with. So if you can only put a certain amount of memory onto the GPU, then you need to start to think about, well, okay, do I need to move all of this data, especially if I'm working with images? Can I resize the images or the video? And in a lot of cases, you typically can. So those are things, techniques that people are using to be able to move, to work with a lot of data, as well as mini batching. If you've got thousands, millions of examples that you're working with, you'll usually break that down into maybe 100 or 1,000 examples that you batch through the actual GPU to process. But most importantly, distributing. You're already doing some type of distribution across the GPU in terms of the computation and the data, but you'll probably start to look at options in terms of using multiple chips in one server or multiple chips across multiple servers to be able to process your data. So you can do things all at the same time across multiple chips, which I think everybody here already understands that concept. The approach in terms of splitting or using multiple GPUs, typically splitting data. You're usually thinking about splitting data, and most of the libraries that you would work with to run a neural net approach it from a splitting data perspective. There are some groups that are looking at how to split neural net models, how to take the actual computations across that model and literally break them out and put them across different chips. You start to hit across more of a challenge of making sure that each chip sees all of the data. And then there's a researcher out of Berkeley who's actually looking at, does the neural net model have to see all of the data, and can I split both? That's about as far as I'm going to go into in terms of how to split the data. But there's some fantastic research out there that you can look into if you find this interesting. So let's talk about branching. So on the GPU chip, you are typically, the smallest component that you're working with is a thread. And you have some control in terms of defining how many threads you're going to break into blocks, and then how many blocks you have in a grid. And the way you would work with this information is that you will potentially divide out your computation across those blocks. Now you have to be aware of the fact, and I think you guys probably get this, that if you're working with a block, that block only wants to do one thing at that time. It doesn't want to do multiple things. It doesn't want you to have a lot of conditionals. It's like, give me one task, give me one computation, and I will do that. And then when I'm done with that, I will move on to the next thing. So this is key because the reality is, when you are building out your program to work with a GPU, you really don't want to run all of your code on that GPU. You want to run the component that is going to receive the best benefit from parallelizing it and doing something in parallel. So in order to do that, or where you're going to find the best benefit, is in this linear calculation. This linear calculation usually is going to be O of n squared or O of n cubed, depending on what you're doing with this neural net and how you're building the structure here. And that you can unroll across the GPU because it's independent. So I have this one layer, for example, with the W1, W2, W3, W4, if you're able to see that. And why I emphasize those was because you've got an example. I've got one picture. That picture's broken into pixels. I've got on the first node, that first node in this top layer, right, a set of weights. and I'm going to apply those weights to that one picture. And so in order to do this, I could pass this through a thread on the CPU and it'll loop through and multiply each value together. Or I could say, hey, this one block of threads on my GPU, take these values, split it across those threads, and then apply, and then do this calculation all at once. Just taking you through this from the standpoint of, this is how you start to think about doing an O of n squared computation and basically breaking it down to an O of 1 potentially. So there's a few other ways and nuances in terms of how you can break this out and how you can think about it, but this is where you're going to get the most gain. Now, in order to work with a GPU, this is an example of some of the code you would potentially leverage from CUDA. And the main steps that you're really going to do to work with the GPU is allocating memory, moving data onto the GPU, actually defining a kernel that will do the computation that you want to run, and then once you have the result in the GPU's memory, moving the data off and back into the CPU memory that you can then further do any kind of calculations you want to do from that point. And syncing is something I think is also something it seems like this group would probably have a sense of, but ultimately you're potentially syncing between the CPU and the GPU or syncing across GPUs depending on the tasks that you've divided out. So I've just listed up here, some example code that you would potentially leverage from CUDA, where CUDA will handle these operations for you. You just need to define the type of pointers and so forth that you want to work with. But if you really want to get serious about this, you don't have to use CUDA's code. You could start writing your own compiler directives, from what I understand. I will let you guys look into that further if you really want to get into the compiler directive point. The nice thing is, there are some packages that have done this for you. They've made this a lot easier for you. There's a lot of packages, actually, that are in existence that allow you to easily define a neural net and then also very easily integrate it with a GPU if you have that on your system. Several of them are in Python. The data science community is pretty heavy in terms of focused on using Python, especially, or Python and R, and also I know Julia is pretty popular. How easy is it? So Café is a pretty well-known and popular one, especially in the commercial space. They have what's called protobuf files. They're like YAML files. So you basically send in sort of, here are my configuration commands. All you literally have to do is say, use a GPU. It'll figure out the rest of it for you. It will handle allocating the space, moving data on and off. It'll handle all of that. As I mentioned in the beginning, I work for SkyyMind. We have deep learning 4J platform. It's in Java. And with Java, you have POM files, which are your config files. And all you have to do is say, which backend do you want to use? And we'll figure that out for you. Theano, Python-based, similar on the command line or in a script, you tell it, use GPU. They have a couple of other things you have to do to configure, since Python's a little bit of a memory hog, to tell it, make sure that your parameters are within a certain space and so forth. But it's fairly simple. It makes this a lot easier for you if you want to pursue and not have to think about writing compiler directives. So now I want to show you guys some code, because I know you're all thinking, I want to see neural net code. Or you're not. Because I also wanted the challenge, and this is going to be fun, of showing you guys how to do neural net code. And I know you're all thinking, oh, we really wanted to see Java. We all love Java, because this is all functional programmers, right? So Java. All right, so I have a class. I have this class that I've defined for, basically, and actually, I'm getting ahead of myself. I have a class, and I'm going to show you, this example that I'm going to show you is called MNIST. Okay, so MNIST, Hello World of Neural Nets. You may have already seen this, especially those who've worked with neural nets before, but bear with me, it's the easiest one to show in a presentation. MNIST is basically saying I've got a bunch of pictures of handwritten digits. I'm going to classify those pictures between 0 and 9. And the pictures are grayscale, so I'm converting these pictures into pixels and converting those pixels into numbers. I've overly simplified this. The numbers are actually 0 through 255. And then the structure I want to build is this structure. It's going to be overly simplified, fully connected. If you're working with images, you know a little bit about structures. You'll usually use a convolutional neural net. I do not have enough time to go through that today, but I will show you a little bit about just a straightforward neural net. And this neural net, 3 layers. I'm actually, when you work with these libraries, a lot of times they only count the hidden layer and the output layer. They don't necessarily count the input layer. So we've got technically 2 layers. But I have 2 layers. My input, I've got a 28 by 28 sized picture. So that means 28 pixels by 28 pixels. That means it's 784. I have 1,000 hidden nodes that are going to do the computations for me. And I have 10 output nodes that will classify between 0 and 9. So with that said, I've got my class, I've got my main method, and that main method will allow me to basically say, and I've got an exception in my main method, which is good. That main method is going to allow me to run this code. And I'm going to define a couple of variables, and these variables are basically allowing me to define one, number of rows by number of columns, so the size of the picture, and then how many examples I'm going to use, 1,000 and 100. I'm going to do a batch size of 100. Okay, so I've got a predefined data set iterator, and this is allowing me to say, okay, this is what my data set is. And so here's the thing. If you've worked with MNIST, MNIST is pretty much easily accessible anywhere. We just have a binary that you can pull in and define how many examples do you want to use and how do you want to batch it. You can pull this in, set it up however you want. But the real meat of this is where you define, and actually, yeah, we're just going to take it off, where you will define the gotta love coding when my laptop does not want to show me the example on my own computer. All right. Live coding, it's fabulous. Bear with me, I'm going to get there though. Okay, so here's what I got, right? I've got this multi-layer configuration. It's just our way of saying this is an object that's going to hold this configuration for you. So the configuration is basically taking in a seed, and I'm going to make this smaller because maybe that'll make it easier. It's going to take in a seed, and the seed is one attribute that we're passing in because when you build out your net, and I create these weights, usually one technique you use to create your weights the first time out the gate is randomizing them. There's a couple of different ways you can randomize them, just to understand that you randomize them. And as you train the model, there's a number of things that you're trying to tune. So when you randomize the weights out the gate, you need to be able to duplicate that. You need to be able to replicate that basically over and over again. So you use a seed to lock that in. If you've done Meldals before, you understand this. I don't think that's a surprise. The iterations are my way of saying how many times are we going to go back into the net and update it as we're trying to get our error to converge to either 0 or as close to 0, or we stop seeing a change in our error rate. So iterations is just my way of saying do it at least 5 times. If I wanted to, I could say do it 1,000 times or until you converge. If you don't converge, then stop after 5. My optimization algorithm is a technique I use to basically say this is how I want you to update the weights that are back inside the net. Stochastic Gradient Descent is that optimization algorithm. It's pretty popular in terms of a technique that's used for neural nets. Look into it. Learning rate is just an approach that you use in terms of saying how much of a tweak or how much of a change will you make on your weights when you go back to make changes. Regularization is a way of preventing overfitting, so you don't want your net to be perfectly modeling exactly the training data you're working with. You need to have some chaos. You need to have a little bit of error in there. And drop connect is another type of regularization that I would say, spend some time looking into it. I think you'd find that interesting as a technique, especially if you've been working with neural nets. All right, so layers. Layers are where I'm going to define how to actually make these layers work, right? So I got the blue layer, and the blue layer is my dense layer. It's my fully connected layer. And so the number of ins are how many inputs are coming into this layer, and it's number of rows times number of columns, so 784 inputs. Number of out is 1,000, meaning I could have up to 1,000 outputs coming out of this layer, so I have 1,000 nodes. And then weight init is just explaining how to initialize. I've got distribute, or just a standard create a normal curve. That's what distribution is. And when you see dist and say normal distribution, that's what we're saying. We're saying create this normal curve and sample from that normal curve to create the weights. And then activation is my activation function. That is better. So activation function, as I mentioned, you do your linear calculation of x times w, you sum it, and then there's an additional function you will apply to this to determine if you're going to have some kind of output. Sigmoid is a popular one, and it's a way of saying, okay, I have a percentage, now squash it up to 1 or squash it down to 0 in terms of figuring out what type of signal you'll send out. There's multiple different types of activation functions you can use when you're working with a neural net. I would just say spend some time reading up on that if you haven't already explored it. There's a lot that you can do with the activation function and different reasons on why you use certain activation functions for certain problems. ReLU is a pretty popular one, and specifically ReLU is short for rectified linear. This is a pretty popular one when you're working with image processing. And dropout is another technique we use for regularization. And then layer 1 is the output layer, and that's basically saying here are my, as you can see in out, the 10 nodes, the 0 through 9 classification nodes that I want to define. Weight init, similar. Activation function in this case is softmax. This is a type of sigmoid. It's a little bit more stable that you will usually use when you're doing some type of classification. And then all I have at the end here is backprop and pre-train. Backprop is just saying go back, do the apply backprop, and pre-train false means there's no predefined weights that I'm using as initial weights. And so with that information defined, in terms of my configuration, I will take that and pass that into a model. And basically, this model is saying, pass this into a model object that's multi-layer network object and create this initial framework. And that's what the model init is doing. And so it's really creating this template. Okay, so that we have the template, we're good to go. What do we need to do once we have the template? All we have to do at this point, because I have my model object template, if you've worked with scikit-learn before, you'll just say fit, and you'll pass in the data. And at that point, you'll say you'll run it, and it will run this. It will take in all the inputs that you've given it. It will go back and loop through it and train on it and come back with a model. And that model at that point you can use to do further predictions and classifications. And to be able to show you that that's going to happen, I'm not sure if you guys will be able to read this, but here's my POM file. I've got jkublas listed here to show you that I am using this as my backend. I am going to run this in my IDE and let that run for a minute and explain a few more things to you guys while it's running. So here's the thing. I just stepped you through just some example code on configuration. And the reality is, yes, that was in our DL4J package, which is open source, by the way. This is not something you have to go buy. But the reality is what I would try to take you through was something that you can see in other code bases. You can look at it in Caffe. You can look at something like that. Maybe not so much in Theano. Theano takes a little bit more finagling, but there's other examples out there like Lasagna, if you like Python, that make it a little easier for you to break down how to do configurations for neural nets. In terms of running this on a GPU, unfortunately, NVIDIA does not provide NVIDIA SMI. This is a way for you to check in your command line if your GPU is running and how is it running. You can use that on Linux or Windows. You could use iStats if you wanted to see, how is your GPU performing. You just have to trust me that it's working. So while it's working, and it's probably done, but I'm just going to talk about a couple things for techniques to troubleshoot. One, just very high level. There's no CUDA-capable device, or there's no CUDA available. Sometimes your system will shut down the CUDA or the CUDA driver, and you'll just have to kickstart it again. This is the command I found that worked on my laptop. What's interesting is Apple is no longer providing NVIDIA cards in their laptops or in their towers. So, you might not necessarily be doing a lot of hardcore development. You won't be doing a lot of hardcore development on Mac or on your laptop even if you had a Mac or you had a Linux. So it's one of those things where I wouldn't say that you have to spend too much time thinking about it. When you're working with a system, you'll probably be working with something through AWS or with Google, but something to be aware of if you're trying to tinker with it at home. If you see kill, you probably need to think about, do I need to reduce the size of my mini batch? Am I, you know, am I blowing out my memory? And if you're trying to work with compiler directives, then you should think about, you know, flushing and how often are you flushing. If it's running really slow, one of the main culprits is really how often are you syncing across the GPU as well as between the GPU and the CPU. And that's really something that you have to look at from a standpoint of if you have direct connection in terms of building out the CUDA interactions yourself, or if you're using a library and expecting the library to handle it for you, you might want to consider looking at a different library. And if you have any kind of I/O error, this is a simple throwaway one. I just threw it up there. But you should look at whether or not you're pointing to the right place where your data is stored. And let's go look real quick. It's done. We got a 69% accuracy. It's not amazing, but you know, it's not bad for about 1,000 examples. And so yeah, I've put this code, and I put a lot of other code, some examples from Caffe and from Theano into a GitHub repo, and I'll show you that link in a minute. I've got a lot of references. I'm going to be posting these slides for anybody who's interested that you know, you're welcome to check out. I also had some people who helped me put together this talk, and I'm grateful for their time. The main things I wanted you to walk away from this talk with is, you know, in terms of neural nets, they're going to play a role in a lot of things around images and language processing, and frankly, they'll start to play more and more role, especially with anomaly detection. And I think those are things that kind of resonate. Where it will resonate with companies and why companies will probably want to spend time and money is because of personalization and customization. If you want to get serious about it, training is the hard part. GPUs will help you with that. GPUs will help you with that because they can do the same thing multiple times at the same time. GPUs have not had a lot of time and attention in terms of development. I was talking to a couple of guys who work with them, and they were explaining to me how there's so much work and effort that's been put into CPUs and optimizing CPUs, and there's a lot of room for growth in that in terms of development around GPUs. So if it's something you find interesting, I'd say check it out. But yeah, this is where my GitHub repository is for where I will have the code posted. I work for SkyyMind. We are open source, as I mentioned. We are currently working on building out Scala bindings. If you want to come and help us out, if you want to do Iterus or Haskell or Clojure, probably not Haskell, but Clojure or any kind of other bindings, bring it. We'd love it. More importantly, Gitter. We have a community. We have like about 600 people on Gitter, and it's just a chat platform that's through GitHub. That get together and we talk about neural nets, developing them, the challenges you have. So if it's something you have questions on or want to explore, you don't have to necessarily use our platform. I think you'd find it just interesting from a community perspective in terms of people to talk to and work with on continuing to develop it. So I'd say, you know, feel free to check it out, and that's all I got. I just want to give a shout out to Strangeloop and Alex Miller and just giving me the opportunity to come out and speak, and I appreciate your time. Thank you.